Traffic detector installation is the most crucial step in the process of implementing traffic detection. Thorough preparation, including reviewing detector theory and application, as well as carefully developing the detector design and plan, can be sabotaged by sloppy installation. Therefore, to avoid detector failure and poor signal operation, do not underestimate the importance of the installation process. In this videotape, as we discuss pre-installation and installation procedures, we will use a specific intersection and loop detector design to illustrate our points. There are a number of pre-installation activities that have to be completed before an engineer can turn over the job to the installation crew foreman or contractor. First, you should thoroughly review all of the design documents. Next, prepare scale drawings of the location. And then, you need to arrange a field visit. A scale drawing of the location should show the correct geometry of the roadway and the exact location of the in-road sensor element in relation to the stop lines. A basic guideline for the installation crew, this scale drawing should include the location of all underground utilities and content of conduit, manholes, power sources, pavement materials, and any electrical equipment that would interfere with the installation. If the detector installation is to be performed by a contractor, the scale drawing becomes part of the procurement package. The completed drawing should be reviewed with the design engineer. This ensures that the loops or probes are located as specified in areas free of any underground hardware that could interfere with detector operation. Prior to finalizing the scale drawing, make a field visit to the location. Once on site, inventory the existing conditions and identify any potential problems. As a result of this visit, you should be able to determine the method for burying cables. Choose the types of equipment required for the installation. Identify the necessary installation permits and licenses. And finally, determine the method of traffic control and rerouting that will take place during the installation. This traffic control and rerouting method includes the position and quantity of barricades and cones. The information obtained from this initial visit is then incorporated into the plan drawings. A second field visit should be made to verify the accuracy of the completed drawings. If the installation is to be performed by an in-house crew, the next step is the estimation of manpower requirements. Studying the plans, determine the scope of the installation work, the amount of time required, and the size of the crew. Often, a crew should perform certain installation tasks simultaneously to reduce the time that traffic is disrupted. The equipment required by an installation will, in effect, be dictated by the detector system type and configuration. Check your handbook for details, including a list of equipment necessary for a typical loop installation. And don't forget that barricades, signs, cones, safety vests, and other devices will also be required to control traffic during the installation. When determining an installation's material requirements, assure that all materials are provided in large enough quantities to avoid any work interruptions. A typical material list for a loop installation includes detector wire, lead-in cable, pull boxes, sealant, cement, sand, or talc, concrete, surge voltage protector, solder, splice kits or equivalent, and spray paint or chalk and line. This completes the pre-installation process. Now, let's discuss installation techniques using our example for illustration. As detailed in this schematic, the loop detector system is composed of one or more wire loops embedded in the pavement to act as a sensor, a splice between the lead-in wire and the lead-in cable in the pull box, the lead-in cable, which is usually in a conduit running to the terminal strip in the controller cabinet, a cable from the terminal strip to the electronic detector unit, and finally the electronic detector unit itself. Installation techniques and theories vary widely among traffic agencies. Construction supervision and inspection by the responsible agency is critical. Let's examine the basic steps to a loop detector installation. Loop detectors are installed in asphalt or concrete pavement by cutting a slot, cleaning and drying the slot, laying in and testing the detector wire, sealing the saw cut, connecting the wire to the lead-in cable and testing it, connecting the cable to the terminal strip in the cabinet, and ensuring that the harness connects the terminal strip to the electronic unit. We will look at each of these steps in detail. Differences among installation techniques usually involve the treatment of the corners where two saw cuts intersect, the splicing techniques, the type of sealant, and the method of applying the particular sealant. Whatever the technique, following accepted procedures will help guarantee the detector's long-term effective operation. Long-term effective operation is the goal. The large number of loop detector failures nationwide has created a deep concern within the traffic engineering community. A number of studies have traced many loop detector failures to a problem with the in-road loop wire, or to the splice between the lead-in wire and cable. These failures are usually due to bad pavement conditions or sloppy installation techniques. Several state agency surveys have noted that at any given time, up to 25% of their installed loop detectors are not operating properly. Now, using our 6-foot by 30-foot quadrupole loop example, we will discuss loop detector installation basics step by step. For more details as well as information on loop installation alternatives, please refer to your handbook. The first step in our detector installation is loop layout. After securing the work zone, carefully mark the pavement for the loop size and shape as detailed on the plans. This loop layout can be accomplished using a lumber crayon, chalk, or spray paint with a template. A straight edge or a tightened string can be substituted, however, as a marking guide. Loop corner treatments vary among agencies. Traditionally, the chamfer cut has been used to ease the stress of a 90-degree corner on the wire. This diagonal cut should be 12 or more inches back from the corner to prevent pavement breakup. As an alternative, however, many agencies choose to core drill holes at the loop corners. This corner treatment, chosen for our example, preserves the integrity of the pavement and the wire. Now it's time to saw cut the slot for the loop wire. This is one of the most time-consuming parts of the installation process. There are many saw types and sizes available. Durable diamond blades and fast-cutting high-horsepower saws are recommended. Water cooling the saw blade increases its life and eliminates the irritating, dangerous, dry-cutting dust. Studies have shown that using a diamond blade, a high-horsepower saw, and water cooling reduces cutting time by 2/3 compared to the less expensive dry-cutting system. The slight increase in initial saw costs can be reclaimed in savings of time, labor, and equipment longevity. Regardless of the type of saw used, it should be equipped with a depth gauge and a horizontal guide to assure proper depth and alignment. Check the depth of the saw cut frequently to assure that it is constant. Although the appropriate depth depends on the number of turns of wire, a minimum depth of 1 1/4 inch and a maximum depth of 2 inches should be maintained. If your saw cut is out of alignment, do not make a second cut near the first. If a second slot is necessary, cut at least 4 to 6 inches from the original slot to avoid significantly weakening the pavement. Finishing the saw cut is an important installation step. Cleaning the saw cut, including removing all jagged edges with a chisel and hammer, should be done immediately after cutting. It is crucial that the saw cut is clean, dry, and free of dust, grit, oil, and contaminants. The recommended practice is to flush the slot clean with pressurized water, then dry it with compressed air. Take care not to blow any debris in the direction of passing pedestrians or vehicles. After the slot is saw cut and cleaned, it is ready for the loop wire. Many contractors have developed their own wire installation techniques and shortcuts. It is important to inspect these procedures during installation. If a wire is damaged during installation, it should be immediately pulled up and replaced. The most commonly used wire size ranges from number 12 to number 16 AWG. In our example, we are using number 14 AWG wire. Stranded loop wire is more likely to survive stretching and bending. The wire insulation must withstand wear and abrasion from shifting streets, moisture, solvents, and oils, as well as the heat of high-temperature sealants. Wire encased in continuous cross-linked polyethylene tubing is popular due to its durability, flexibility, and heat resistance. Some agencies pre-wind and bind loop wire to the exact specifications in their shops, making a prefabricated loop to transport to the site. Best suited for smaller loops, this procedure significantly reduces on-site installation time. Several detector manufacturers offer a preformed loop assembly that can be placed in existing pavement slots or installed in other ways during the construction of new roads. Although the initial cost of the preformed wire is higher, the total installed cost is often lower than that of standard loops. A metal sheathed loop, known as mineral insulated or MI cable, is particularly good for hazardous locations or difficult environments. This factory-assembled loop has several advantages, including an excellent shielding system. Wire insertion is the next loop detector installation step. The loop must be one continuous wire, from the pull box through the curb, around the slot the correct number of turns, and back to the pull box. Check the supply reel to make sure there is enough wire before beginning. It is very easy to lose count of the number of turns you have inserted, particularly with 4 or more turns. Pre-wound or preformed loops can eliminate this possible confusion. All loops should have enough turns to provide at least 100 microhenries inductance per loop. This is a simple rule of thumb for determining how many turns are needed to provide the required inductance. If the loop perimeter is under 30 feet, use 3 turns of wire. If the loop perimeter is over 30 feet, use only 2 turns of wire. When a loop is placed in a concrete roadway and crosses a pavement joint, particularly an expansion joint, the wire can be damaged as the concrete slabs move. The joint where the road surface meets the curb line can also cause problems through horizontal and vertical shifting. There are 2 basic treatments for crossing a pavement joint. One method is to encase the wire crossing the joint in some type of conduit, from a rubber garden hose to flexible or rigid plastic tubing. A second method is to provide extra wire at the pavement joint. For example, you can make a 2-inch diamond cut at the joint to allow an S shape of extra wire. After inserting the wire, you will have 2 lead-in wires from the beginning and the end of the loops. These 2 wires should be twisted together to form a pair from the loop to the pull box. Using a twister is a lot faster than doing this job by hand. To avoid crosstalk, you should twist the wire between 2 and 5 times per foot. And if you are installing adjacent loops, make sure you twist all the lead-in wires in the same direction. Typically, the twisted lead-in wire extends from the loop across the curb or shoulder to the pull box. The lead-in wires from adjacent loops should be run to the pull box in separate slots to avoid crosstalk. At intersections with curbs, the joint where the road surface meets the curb line can cause problems for the twisted wire through horizontal and vertical shifting. Using a jackhammer drill or punch-type tool, make a hole in the curb and install a watertight, flexible conduit. At intersections with shoulders, as in our example, dig a trench from the pull box location to the pavement. Then, at a 45-degree angle, core drill a hole at least 6 inches from the edge of the pavement into the trench. Next, cut 1-inch, thick-walled PVC conduit to the correct length and place in the core hole. Run the wire through the conduit and then the conduit above the drainage line to the pull box. Then place duct seal at the pavement end of the conduit to keep out saw-cut sealant and to facilitate any future maintenance on the wires. Refer to your handbook for other curb and shoulder crossing techniques. The next step is the installation of the pull box, also called the splice box, the junction box, and the hand hole. The pull box houses the splices between the lead-in wires from the loops and the shielded lead-in cable to the controller cabinet. Made of concrete, plastic, metal, or fiberglass, these pull boxes are also required at intervals in especially long runs of wire. It is essential to provide all pull boxes with adequate drainage when installed. Most installations utilize a standard number 3 or number 5 pull box. For our example, we are using an existing number 1 pull box. The conduit, usually a 1-inch conduit carrying 1 or 2 twisted wires, is connected to the pull box during its installation. At the roadway end, the conduit should be terminated 2 inches below the pavement surface. To protect the wires, attach a non-metallic bushing and tape the wires for several inches on each side of the bushing. And remember, it is important to tag each wire identifying loop number and the start or finish of that loop. In our example, we are using colored tape for tagging. Now that you have inserted the wires, installed the pull box, and terminated the conduit, you must test the loop. A loop tester instrument capable of checking the wires' induced AC voltage, the inductance in microhenries, and the resistance of the conductors in ohms should be used. In addition, you should check the integrity of the wire insulation using a megometer or megger. Applying a 500-volt megger between each end of the lead wire and the nearest electrical ground should produce a reading of at least 100 megohms under any condition. The loop installation is acceptable if, when measuring induced voltage, there is no deflection of the voltmeter pointer, when the resistance to ground of the loop exceeds 100 megohms, and when both the inductance reading and the loop resistance reading are both within 10% of the calculated values on the wiring diagram. These metered values should be written on the wiring plan or on an inspection report for future testing and maintenance. The next step in loop detector installation is sealing the saw cut to protect the wires from breakage and moisture. It is important to match the proper sealant and the sealing technique to the type and condition of the roadway at your site. The sealant should be hard enough to prevent wire damage from street debris and flexible enough to prevent cracking due to pavement shifts. Also, the sealant has to withstand corrosion by road salts, gasoline, and engine fluids. Sealant applications are divided into cold pour sealants, such as resins and epoxies, and hot pour sealants, such as hot pitch and asphalt. Most states specify which sealants work best under their particular climate and geographic conditions. There are 3 common methods of applying sealant which appear to be equally effective. The first method specifies a layer of sealant in the bottom of the saw cut before the loop wires are inserted in the slot. Then a second layer of sealant is applied over the wires to fix them in the middle of the slot. The next method calls for simply applying sealant over the wires which lay at the bottom of the slot. The last and following method reduces stress on the sealant by requiring less sealant in the slot. First, a backer rod, usually a polyethylene rope, is forced into the slot over the wires. Then the remainder of the slot is filled with a shallow layer of sealant. Whichever method is chosen, apply enough sealant to fill the saw cut completely. A trowel or similar tool should be used to remove any excess sealant. Remember, overfilling, underfilling, and air bubbles in the sealant can all cause detector failure. Finally, some agencies coat the newly applied sealant with sand or talc to prevent tracking the sealant during its curing stage. It is critical that you plan your installation process in such a way that the saw cutting, wire installation, and loop installation are completed within the same day. Saw cuts should not be subjected to traffic flow. The next critical step in the installation process is the splicing of the loop lead-in wire to the lead-in cable. Located in the pull box, this should be the only splice in the loop system. There are 2 basic steps to the splice: the physical connection of the wires and the environmental sealing of the connection. To make the physical connection, you must first strip away about 8 inches of the outer covering of the lead-in cable. Then clip one of the cable's 2 wires about 3 inches shorter than the other to offset the soldered joints. Next, strip away about 1.5 inches of insulation from the cable wires and the loop lead-in wire. In our example, the new loop is being spliced in series with an existing loop. To physically connect the wires, there are 2 preferred methods: twisting and soldering, or crimping and soldering. Taking care to connect the correct wires, either twist the wires together end to end or crimp them with a non-insulated butt connector. If you choose to crimp the wires, we recommend a high-quality pressure tool for a uniform crimp. Whether twisting or crimping the wires, always solder the connection using 60-40 resin core solder. This soldering provides a connection with lower resistance and less chance of damage by corrosion. Once the wires are firmly spliced, you must seal the connection against such things as weather and moisture. There are a variety of environmental sealing methods, including heat-shrinkable tubing, tape and coating, special sealant kits, as in our example, pill bottles with slot sealant, and special sealant forms. For more information concerning these methods, please refer to your handbook. Any of these methods is acceptable if it provides a sound environmental seal. Installing the lead-in cable is the next step. However, our example uses an existing cable. Generally, one cable is placed in an underground conduit from the pull box to the controller cabinet. Whether by itself or within a waterproof conduit, the cable should be placed in a trench at least 18 inches below the surface. Next, the trench should be backfilled with up to 6-inch layers. Then, use mechanical tampers to compact each layer to the density of the surrounding ground. The lead-in cable will end inside the controller cabinet at the field terminal strip. Most manufacturers recommend grounding the cable at the cabinet. This entails connecting the shield to the terminal and insulating the end of the cable in the pull box. This allows any electrical disturbance or interference to be safely grounded without affecting the loop lead-in cable. For example, loops receive a voltage surge whenever lightning hits the ground nearby. Back-to-back Zener diodes or metal oxide varisistors usually provide adequate protection from these surges. After all the loops and cables have been installed, it is time to conduct the tests again. The results of these tests should be recorded on the installation data sheet. Also, any modification made to the original plan drawings should be noted and dated. The exact readings from the tests and the modified plans should be verified by an inspector. Finally, these as-built plans should be stored for future maintenance or repair work. Now that we have discussed the basics of loop detector installation, let's look briefly at the installation of the microloop. The pre-installation activities required for the microloop, a type of magnetic detector, are identical to those of a loop detector. There are differences, however, in the step-by-step installation procedures. Typically, the installation of a microloop and a magnetometer involves the placing of probes in cored holes in the roadway. The best depth and layout of these probes depend on the type of detection required by the site. After securing the work zone and marking the detection area, use a magnetic field analyzer at each marked probe location. This verifies that the area is free of any elements that would degrade the detector's performance. Next, drill holes with a diameter that is 1/8 inch larger than the diameter of the sensing probes or the PVC pipe if lining the holes. It is imperative that the microloop or magnetometer probe should be mounted in a stable, vertical position. Lining the hole with PVC pipe ensures that the probe will remain vertical if the hole walls collapse. The required depth of the hole should be defined on the construction plans. Then saw cut, clean and dry the slots for the connecting cable to run from the pull box to the probes. The pull box for the microloop is installed in the same manner as a loop detector system pull box. As stated, each probe should be placed vertically in the hole with the cable ends at the top. To make sure that it is securely supported, pack sand around the probe. Now it is time to install the cables. Seat the cable in the sawed slot, allowing 5 feet of slack in the cable at the pull box. Each cable should be identified by lane or by probe. Then, using a volt-ohm meter, check that the series resistance or continuity of the probe and the cable is within 10% of the calculated value. To ensure that there are no breaks in the probes or wire insulation, you should also check that the resistance to ground value is high. Do not, however, use a megger to check this resistance because the high induced voltage will destroy the probe. Now that these sensing element cables have been installed and tested, they need to be spliced with the lead-in cables to the controller cabinet. All connections should be soldered, insulated, and sealed in a waterproof manner. Also, microloop detectors perform best when the cable shield is not terminated at both ends and is insulated against contact with other conductors. Before filling in the holes and the slots, it is important to test the system one more time at the controller cabinet. In this test, the series resistance will be higher due to the added resistance of the lead-in cable. You should also make an operation check at the controller cabinet. If the system tests correctly, seal all the holes and slots using the same methods employed for loop detector installation. Generally, magnetic detector pre-installation activities are very similar to those of a loop detector and the microloop. The actual installation of magnetic detectors and magnetometers, however, is closer to that of the microloop. Please refer to your handbook for details. Now that we have examined basic detector installation techniques, let's proceed to Section 4 for a discussion on detector maintenance.